of this lecture, today I will see some relationship between prime ideal and maximal ideal. And this relationship actually very important for higher study, also for any competitive exam. First relationship, when R is CRU, means commutative ring with unity, then every maximal ideal of R is prime ideal. That means when the ring commutative ring with unity, then maximal ideal always imply prime ideal. But converse not true. In Z, 0 is a prime ideal, but not be maximal. But when the ring is commutative ring with unity, then if the ideal is maximal, then always maximal ideal is prime ideal. But converse not true. That means in a commutative ring with unity, every prime ideal may not be maximal ideal. But in integral domain, every non-zero prime ideal be maximal ideal. That means when the ring is integral domain, then every non-zero prime ideal always be maximal. Also, in a finite CRU, a non-zero ideal is maximal if it is prime. Because we all of us know, if R be a commutative ring with unity and P be an ideal of R and P not equal to R, then P is prime if R mod P is an integral domain. And if R be commutative ring with unity and P be non-zero ideal of R and P not equal to R, then P is maximal if R mod P is finite. If R mod P is filled. That means when R mod P is isomorphic to field, then P is maximal ideal. And when R mod P is isomorphic to integral domain, then P is prime ideal. And in finite CRU, a non-zero ideal is maximal, it is prime. Because in finite CRU, R mod P, if P is prime, then this is isomorphic to integral domain. And since this integral domain is finite, and we all of us know finite integral domain imply this is field. So obviously P is maximal. That means in finite CRU, a non-zero prime ideal always be maximal. Otherwise, in CRU, a maximal ideal always be prime ideal. But in commutative ring with unity, every prime ideal may not be maximal ideal. But when the finite CRU, that means R mod P, if this is prime ideal, if the ideal is prime, then that implies this is always be maximal, because then R mod P is isomorphic to integral domain, and since here given the ring is finite, that means integral domain would be finite, and finite integral domain imply this is field. Field imply obviously this ideal P is maximal, that means in finite CRU every prime ideal always imply this is maximal. Okay, this relation actually very important relation. In PID every non-zero ideal is prime if it is maximal. That means in PID every maximal in PID prime ideal always imply maximal. Prime ideal always imply maximal ideal. Actually, in a PID, being a prime ideal and being a maximal ideal are the same. This is only true for PID. And another relation, when the field is finite, when commutative ring with unity, finite commutative ring with unity, then prime ideal means this is always maximal. But otherwise, for general case, maximal may not be always prime. Just recall, we know Z is PID, but the polynomial ring ZX is not PID. That means when F is field, then Fx is PID. And combine these two results, if R is a commutative ring with unity such that Rx is PID, that imply if Rx is PID if R is a field. That means when R is a field, then Rx is always PID. And if since Z is PID but Zx is not PID, that means when Rx is PID, if R is a field. This is because, and this is why, because assume Rx is a PID. Rx is a PID. Note, Rx has identity if R dash. We all of us know. Since Rx has a subring which is isomorphic to R, then R must be integral domain. Because otherwise, if R not be integral domain, then this, since Rx is PID, then Rx contains zero divisor. This is not possible. And in Rx, X is a prime ideal since Rx modulo X is isomorphic to R. And since Rx is PID and X is a prime ideal, in PID every prime ideal is maximal ideal, that means X is a maximal ideal. And since Rx modulo X is isomorphic to R, and here X is maximal ideal I have got, that means obviously this R is a field. Next I will see some result about these properties. First question, let C01 be the ring of all layered valued continuous function on closed interval 01, and let A equal to F belongs to C01 such that F of 3 over 4 equal to 0. Then which of the following statement are true? Option 1, A is ideal in C01 but is not a prime ideal in C01. Option 2, A is prime ideal in C01. Option 3, A is a maximal ideal in C01. Option 4, A is a prime ideal in C01 but not a maximal ideal. In my previous video I had seen in C01, if kernel is F belongs to C01 such that F vanishes at any point, if F of A equal to 0 and A belongs to C01, then this is isomorphic to real number. Okay, notice here given f of 3 over 4 equal to 0. Here 3 over 4 be one point. Then that imply, since this is isomorphic to real number and real number be a field, so obviously C01 is a multiplicative ring with unity. So in C01 this type of ideal is always maximal ideal, and since C01 is the commutative ring with unity, C01 is CRU. So in CRU every maximal ideal always be prime ideal. So these imply this is also prime in C01. That means A is a maximal ideal and A is a prime ideal. These two options are right option. Now I will see one question which had come session net December 2019 exam. The question is IV an ideal which of the following statement are true. Option 1, I is principal ideal object. Option 2, I is prime ideal object. Option 3, if I is a prime ideal object, then I is a maximal ideal object. Option 4, if I is a maximal ideal object, then I is a prime ideal object. At first think oneself. Here, we all of us know Z is a commutative ring with unity, and every ideal object generated by single element. So Z is a PID. That means option 1 is a right option. Z is a principal ideal. I is a principal ideal object. Z is a commutative ring with unity, and let I be an ideal object. Z is PID. That means every ideal object is a principal ideal which is generated by some element A in Z. So Z is a PID. Here every ideal generated by non-zero element A. So Z is PID. We all of us know this is. So option 1 is the right option. Option 2, I is the prime ideal. Is every ideal object is prime ideal? We all of us know. Prime ideal object look like NZ type where N is prime. Because when Z mod NZ, then this is isomorphic to Zn. When N is prime number, then this Zn is integral domain as well as field. So since Zn is integral domain as well as field, so Nz is prime ideal as well as maximal ideal. So I is a prime ideal. Every ideal is prime ideal. This is not true. When N is a prime, then this is true. Consider the ideal 6z. Is it prime ideal? It means 6x where x belongs to Z, and 6 equal to 2 times t, 3 which is belongs to I. Here consider this is A, this is B. AB belongs to I, but neither 2 belongs to I nor 3 belongs to I, because ideal is look like 6x type. So this ideal is not prime in Z. So I is a prime ideal object. This is always not true. Next, if I is a prime ideal object, then I is a maximal ideal object. That means is prime ideal imply maximal ideal object? For this, consider I equal to 0 ideal. 0 ideal means only the set containing 0 element. Now AB belongs to I means, since we have to prove this is the prime ideal, AB belongs to I means AB equal to 0. Since Z is an integral domain, so AB equal to 0 means either A belongs to 0, that A equal to 0, that means A belongs to I, or B equal to 0, that means B belongs to I. So I equal to set containing 0 element is a prime ideal in Z. Is it maximal ideal also? No, because I equal to ideal generated by 0 is also contain, this is not equal, ideal generated by 2 which is contained in Z. Similarly, I means here ideal generated by 0 contain in ideal generated by 3 which is contained in Z. Similarly, I contains many ideal. So ideal generated by 4, ideal generated by 6. So this is prime ideal. Ideal generated by 0 is a prime but not maximal. So option 3 also not true. Every prime ideal object is not maximal ideal. Option 4. If I is a maximal ideal object, then is I is a prime ideal object? This is true. Since Z is a commutative ring with unity and given I is a maximal ideal, object, that imply I is a prime ideal object, since every maximal ideal in a commutative ring with unity is a prime ideal. So option 4 also right option. That means option 1 and option 4 is a right option. I will stop here. In my next video, I will discuss some more questions about the properties of maximal and prime ideal. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.